Hello, I'm George Matthew. Today I'm going to talk about SLACC, Simion-based language agnostic code clones, co-authored by Dr. Chris Parnan, Dr. Katie Stolley, and me. What are code clones? Code clones are snippets of code that are identical to each other. If these snippets have similar functionality, they're called behavioral or functional code clones. Consider the example of two interleaving arrays. Here are three Python functions that implement this functionality. The first uses an external library to chain two arrays. The second uses the built-in zip function that returns an element from each array. Finally, the third function uses the inbuilt range function. The first two functions have different syntax but exhibit identical behavior, while the second and third functions have similar syntax but exhibit similar but not identical behavior. You see, the first two functions fail to interleave arrays of different sizes, while the third function handles this case. The same functionality can be implemented in Java as well, as you can see on the right. Although the syntax of this implementation is different to all the Python implementations, we can see that it has similar behavior to PyInterleave1 and PyInterleave2, and identical behavior to PyInterleave3. So, why are code clones significant? For starters, most open source projects on GitHub have source code in 2 to 5 programming languages. This could result in similar functionality across languages within the same repository. Thus, identification of functionality in one language in a repository can help a programmer replicate the functionality in another language. A study by Mayer and others in 2017 found that an engineer who makes an open source contribution knows 7 programming languages on an average, and knowledge of one programming language can help learn a new language faster. This can also be applied in an educational setting where cross-language learning strategy is the most common approach taken when learning a new programming language. Traditional code clone detection is limited to syntactic behavior and between similar languages like Java and C#. They are either based on a predefined set of rules or an underlying embedding scheme like a vector representation. As a result, they cannot be applied to languages that are drastically different to each other. We propose SLACC, which is a code clone detection tool based on input-output behavior, which identifies clones between partial and whole methods. SLACC is the first technique to detect clones for dynamic type languages like Python. It does not require annotations or manual efforts such as seeding test inputs or input files. Critically, unlike any other clone detection technique, it can detect semantically similar clones across multiple programming languages and type systems. We'll now walk through SLACC. To help us in understanding different phases, we will use the interleave example which we described earlier. In the first stage, SLACC crawls through a repository and extracts source code. This can be from GitHub, Google CodeJam, etc. The next stage is segmentation. Source code is first snipped by recursively extracting subtrees from their abstract syntax trees using a sliding window with configurable size. Here we show that two such subtrees from the AST of the interleave function. The extracted snippets are then converted into functions by identifying the arguments and possible return values. For statically typed languages, these can be inferred from the generated snippets, while for dynamic typed languages, they are inferred by the data flow analysis of constants in the source code. The next stage is generating inputs for snip functions. Inputs are generated using a gray box testing based strategy based on the types of the function arguments. In case of primitive types, the inputs are sampled from a multimodal distribution constructed from the constants of that type in the source code, while for objects, arguments are recursively generated for each argument in its constructor. The snip functions are then executed over the generated inputs in an isolated environment, and its return values and exceptions raised are stored. Finally, the functions are clustered based on generated inputs and executed outputs and exceptions using a representative-based clustering approach. In this approach, clusters are built by a linear scan of the functions. Functions are clustered only with the cluster representatives rather than all the functions in the cluster. This significantly reduces the runtime of the clustering by an order of magnitude. Here are the clusters for the interleave problem on different solutions. As we can see, functions interleave and PyInterleave3 are behaviorally clustered together since they are functionally identical. Also, functions PyInterleave1 and PyInterleave2 are clustered together since they are also functionally identical, but they only succeed in performing the interleave functionality partially. That is when the inputs are of the same length. We can observe this behavior in the first loop of the interleave functionality implemented in Java. As a result, it is clustered along with PyInterleave1 and PyInterleave2. That said, when the input arrays are of the same length, all the four functions behave similar to each other and are clustered together. SLACC also managed to find other interesting cross-language clusters. Some of them are listed here, like on the left, there are snippets of code that compute the area of the polygon. There is also functions to read a file of integers and finding the minimum of an array as shown on the right. These are some examples of the clusters where we can associate a name to the functionality. There are other clusters detected by SLACC where it cannot be named or is a combination of multiple functionalities. Our experiments were performed on the valid Python and Java submissions from the fifth round of Google Code Jam for the years 2011 to 2014. We compared SLACC against Hitoshi IO, which detects Java clones at method level granularity in JVM-based languages using input-output behavior. Unfortunately, we did not find a functional clone detection technique for Python and cross-language code clone detection. Hence, we compared it against an ASD-based clone detection technique, which has been used as a benchmark earlier. To evaluate SLACC, we used two sets of metrics. First was the number of clones detected in a corpus. Second was the precision of clone detection. This is computed by running the detected set of clones on a new set of randomly generated inputs and checking how many of the clones held. The experiments were executed on ArcHPC distributed system by NCSU. Based on our experiments, we found that SLACC identified 135 method level clones compared to 20 by Hitoshi IO at a precision of 86.7% and 30.7% respectively. This was our first research question where we compared SLACC in statically typed languages. SLACC is also the first technique to identify behavioral clones in dynamic typed languages. We found that in Python submissions, SLACC was able to detect clones with a precision of 87.3%. Finally, for the third research question, SLACC was able to identify cross-language code clones between static and dynamic type languages at a precision of 94.2%. Based on the study, we can draw some implications. Firstly, it is easier to identify succinct behavior. This is because SLACC identifies more code clones compared to Hitoshi IO that operates only at the method level. And as we know, most methods encompass multiple behaviors. Next, we can achieve lower false positives by using more inputs as observed due to the higher precision on SLACC. For example, Hitoshi IO used one test file, while SLACC uses 256 inputs, and after 128 inputs, we observe a sharp decrease in the false positive rate. That said, if inputs are generated via random generation, we would need 4090 inputs for this corpus compared to 256 inputs required by gray box input generation technique and sampling from multimodal distribution employed by SLACC. SLACC is still a work in progress. Post our ICSI submission, we have extended support for Pandas library in Python and the R programming language. We are currently working on expanding SLACC from clone detection to code search by augmenting syntactic search with behavioral similarity. Later, we hope to expand SLACC in other areas like transition of code based on behavior and identifying differences in similar code snippets. Thank you for listening to this talk. You can read our paper on arXiv or feel free to use and contribute to our work on GitHub.